Hey folks, we're going to take a look at magnetic field strength around a wire that is carrying current. This equation is taken right off of your equation sheet to identify the terms. B is the magnetic field strength. It's given in Teslas. Tesla is a unit. The reason why that unit exists is because the guy who figured this out was named Nikolai Tesla, and since his last name was Tesla, thus the unit. Mu naught is a constant. It's 4 pi times 10 to the negative 7th Tesla meters per amp. It's the vacuum permeability. Loosely translated, that means it just talks about how effectively a magnetic field can move through a vacuum. I is current in amps, R is your distance in meters. A few things I want to point out about this equation. If you notice, the denominator here is 2 pi r. 2 pi r is the circumference of a circle. And the reason why that ends up in our equation is because the magnetic fields around a wire actually take the shape of a circle. So if I had a wire carrying current to the right, shown like this, my magnetic field lines would be coming out above the wire. They would wrap down in front of it and then go behind the wire again. And they would do it such that they are forming circles around the wire. So that explains where the 2 pi r comes from. I do want to point out that as I've drawn these three circles, you would definitely have other concentric circles that were further out around the wire. And a good example is what's shown right here in this image. Now, to determine the direction, we use what we call the right-hand rule, where you are using your thumb and your hand. Imagine your pencil is the wire. So if you look at this diagram, have your pencil pointing vertically. And since the current is is going upwards, when you grab your pencil and you grab it with your right hand, you want your thumb pointing upwards. Now pay attention to your fingers as you go from knuckle to knuckle to knuckle to fingernail. So starting at your hand, going through all three of the knuckles to your fingernail, it kind of makes a circle around the pencil. Imagine your fingers are the magnetic field lines, and they're running from through the knuckles into your fingernail. So that's ultimately what this image is trying to show you. We'll run one math example for this and then call it. The goal is to determine the magnetic field strength 20 centimeters away from a wire carrying 15 amps. So B is mu naught over 2 pi times I over R. Now, mu naught itself is 4 pi times 10 to the negative 7th. So what happens is, since we in this class are always going to be dealing with vacuum, this whole piece here, the mu naught over 2 pi, this is always going to simplify to simply 2 times 10 to the negative 7th. The current was 15. The distance was 20 centimeters. We convert to meters, so 0.20. At this point, it's a matter of grabbing a calculator, going 2 times 10 to the negative 7th, multiplying it by 15, dividing it by 0.2, and I get 1.5 e negative 5 Teslas. Magnetic fields in general are pretty small. To give an idea, the Earth's magnetic field is about 4.5 times 10 to the negative 4th. So it's when you get small magnetic fields that are on the order of milli or micro, that's usually a good sign that you did it right. Some problems, you might have a single or a double digit magnetic field. That's fine too. But if you're getting something where you're getting thousands or millions of Teslas, odds are you've probably done something wrong in the calculations.